All right, hello everyone. Welcome to the video for section 4.4. This will be a one-part video. This is a fairly short topic, but one that I think is super interesting. All right. So it's about the mean value theorem, and we'll get to that in a minute. But first, I want to talk about something called Rolle's theorem, which is kind of the basis for the mean value theorem. So in Rolle's theorem, here is kind of the setup. So we have a function f that satisfies three things. So it's continuous over an interval, it's differentiable over that interval, and then for the endpoints of that interval, so notice that we've got the endpoints labeled as a and b here. The output values at each of those are the same. So here we have f of a equals f of b. And we're told that if we have those three things being true, then there is some number c on that interval such that the derivative evaluated at that number c is equal to 0, which is kind of a neat thing. And I'm going to draw a picture here so we can kind of see why this is. So draw a graph. And of course, the graph doesn't have to look exactly as I'm about to draw it, but just so we can get an idea. So here's our left endpoint A, our right endpoint B, and then we have a graph that goes in between those two. Now, the other thing we're told is that f of a equals f of b. So let's call this value right here where that red line is. That'll be where f of a is, and also where f of b is. And then in between, we're told that the function is continuous and it's differentiable. So that means it has to be one continuous curve, can't have any sharp points or places where there's vertical asymptotes. So it's going to look something maybe like this. Okay. And notice in that, do we have any points where we can obviously see that the derivative is equal to 0? And hopefully you would agree with me. Yeah, there's a few, right? We see that there's one here, and one here. So those would all be candidates for this value c, where the derivative is equal to 0. All right, let's try another one. Or just draw a different type of graph here. Let's say that the graph looked something like this. Well, do I still have a point where the derivative, the value of the derivative is equal to 0? Hopefully you're saying yes, right? Because here at the apex, kind of the top of that curve, is another place where the derivative will be equal to 0. So kind of the moral of the story here is regardless of how I draw the graph between the points A and B, as long as it's continuous and differentiable, there's always going to be a point where the derivative equals 0. Okay, and that's because, I should highlight, that's because the output values of the two endpoints are the same. All right, I'm going to try one more. So what now if I draw the graph like this? Okay. Does this theorem still hold? Do we still have a point where the derivative equals 0? Oh, right, yeah, we do, because notice we have a horizontal line, and we know that for a horizontal line, at every point along that, the derivative is equal to 0. So we know really any point along there can be that value for c that we're looking for. Okay? All right, so that's Rolle's theorem. Now, Rolle's theorem is a specific case where the endpoints, again, of the interval have the same output values, and so we know there's a place where the derivative equals 0. So this leads into the mean value theorem, which is a more general version of that. So here's how the mean value theorem works. So we have a function f that satisfies a couple of conditions. So the first one being, that it is continuous on that interval and differentiable. So same first two conditions as the previous theorem. And if we have that, then what we know is that there is some number c in the interval between the two endpoints such that the derivative evaluated at that point is equal to this thing here. And what do you recognize that thing? What does that look like? What is that? Oh, right. That's the slope of a line between the points A and B, right? So let's kind of draw a visualization of that. So I'm going to draw it over here. So here again is my coordinate axes. Here are my points A and B. And this time we're not requiring that f of A and f of B be the same. So I'm going to say that f of A, for example, is going to be up here. F of B is down here. And then I'll draw a graph in between the two. And the graph could look like lots of different things, maybe like that. And what this function, or what this theorem is saying, is now if I connect the line between the points f and A and f of B, so that's what the dotted green thing is supposed to be, and I find the slope of that line, which is what this is, then there is some point in between A and B where the value of the derivative, or the slope of the tangent line, is going to be equal to the slope of that point. And my graph is really poorly drawn, but I'm going to guess that probably in this case that point would be probably somewhere up here in this upper corner. Looks like we might be able to draw a tangent line that's parallel to the green line. Okay? So I think that's another pretty neat thing, that as long as you're continuous and differentiable, you have this property. This equivalence statement down here, that f of B minus f of A equals f prime of C times B minus A, that's another way to think about the mean value theorem. I'd say that's a little less common than the one at the top or the one above that, but it's another one nonetheless. Okay, so let's use this. And this is one of those instances where the professor says application of the mean value theorem, but what they mean when they say application is application to math, not to anything else, which is probably less exciting for you all, but it's exciting for me, and I guess that's all that matters, right? Yeah. Okay, so we have this function v of t equals t cubed minus t on the interval 0 to 2. We need to find the average rate of change on that interval. So we'll go ahead and do that. So first thing we need to do is evaluate the function at the endpoints. So we'll do v of 0, which looks like it would give us 0. And v of 2, which would be 2 cubed. It's 8 minus 2 is be 6. And then we can find our average rate of change, or our slope between those 2 points. So remember that that's going to be, in this case, v of 2 minus v of 0 all over 2 minus 0, which will give us 6 minus 0 over 2 minus 0, which would give us 6 over 2, which would just be 3. Okay? And recall, again, according to the mean value theorem, because this function is continuous and differentiable over the interval we're looking at, you could confirm that by either graphing it, or we also know it's a polynomial, so that tells us that. So we know there exists some value c between 0 and 2 where the derivative evaluated at that point is equal to 3 here. And so that's what the second part of this problem is, to find that value where that occurs. So what we'll do, go ahead and take our derivatives. So find v prime of t, 3t squared minus 1. Set that equal to the value we have there for the slope. So 3, not that at all. 3 equals 3t squared minus 1. Solve for t here. Can do that by adding 1 on both sides. So we get 4 equals 3t squared divided by 3 on both sides. And I'm sorry, I'm squeezing this in down here. And so there we get t squared equals 4 over 3. And I'm going to go ahead and make myself a little bit more room here to finish this. Okay, so again we have t squared equals 4 over 3 square root on both sides, do the plus or minus. So we get t equals, and we're taking the square root of a fraction. Remember, we can break that into the square root of the top over the square root of the bottom, so we can write this as plus or minus root 4 over root 3, which should give us plus or minus 2 over root 3. And then if we want to, we can rationalize that, excuse me, so we don't have a root in the bottom, so we can multiply by root 3 over root 3. And when we do that, we end up with plus or minus 2 root 3 over 3 as our candidates for the value c here. And if you recall, the interval we're working with is 0 to 2. So we're not going to use the negative answer here. So our value for c then would be 2 root 3 over 3. And just plugging that in the calculator really quickly, we see that 2 root 3 over 3 is 1.155, so that is in our interval. Okay, so that would be the point where the slope of the tangent line would be the same as that average slope calculation. All right. Now, I just talked about how that application we did was just an application to math. So what I wanted to do now is try to do an actual application where this might be used in the real world. Okay? And you might think this is hokey, but I actually think this is kind of interesting. So here is the situation. So suppose that a car is equipped with an easy pass, and some of you may have some of those on your car here in Washington. Sometimes you use those to go across, or I guess we call them good to go, but we use them to go across the Narrows Bridge. So let's say that drives through a toll plaza in Carlisle, Pennsylvania, which is at mile marker 26 on the Pennsylvania Turnpike, to the one in Valley Forge, which is at mile marker 326, and that takes 1 hour and 15 minutes. A few days later, the driver receives a speeding ticket in the mail, and the question is, how did the authorities know? Sorry. How did the authorities know the driver was speeding? Okay, so let's take a look at this. So we can use the mean value theorem here to figure this out. Okay, so in order to use the mean value theorem, what we first need to do is get some points. Let's see, is there some points we can make out of this? Well, one thing I see is for the first kind of piece of information we're given, we're told that the car starts at mile marker 226, and then after an hour and 15 minutes, it's at mile marker 326. So I'm going to go ahead and make 2 points that look like this. One is going to be 0, 226. And the other is going to be 1.25, 326. And what I'm thinking here is that at time 0, so at 0 hours, the car was at 226 miles. And then at time 1.25 hours, so 1.25 hours, that's 326 miles. Okay. So now that we have that, we can find our average slope, or average rate of change over that interval. So we can do that by doing m equals, we could do 326 minus 226 all over 1.25 minus 0. When we do that, it looks like we end up with 100 over 1.25, which then is going to give us 80. And if we think about the units on this, these numbers on the top, the 326 and the 226, those are both miles. The 1.25 and the 0, those are both hours. And so that tells us that these units here are miles per hour, right? So the average rate of change, or really the average velocity of this car over that hour and 15 minutes, when they're going from 1 mile marker to the next, was 80 miles per hour. Now, you, first of all, just seeing that, say, okay, well, there's no way that the person averaged 80 miles per hour without breaking the speed limit, right? Unless they were like in Montana. I don't know if y'all know, but Montana has 80-mile-an-hour speed limits. But also remember, the mean value theorem tells us that on the interval we're looking at, so between 0 hours and 1.25 hours, there is a place where the value of the derivative, or really the average, the slope of the tangent line, at a particular point was equal to 80 miles per hour. And putting this in context, that tells us that there's a point where the instantaneous velocity of the car was 80 miles per hour. Okay, so that is how the authorities knew that the person was speeding. Pretty cool, huh? I thought you'd think that. All right, that's all for now. Thank you for watching.